All right, so I'll give just a very brief update on global climate variables, just briefly, and then we'll look at the observed trends in Iowa climate, and then take a peek at what the future climates are projected to be. The sources here are the 4th National Climate Assessment on the left, the Climate Science Special Report, which is in the middle. That's the first volume of the 4th National Climate Assessment, 2017, and the second volume of the 4th National Climate Assessment is on the right. That's 2018. So these are the basis for many of the plots, and you can go and look at that. You can find more context. The websites are located there. So the iconic graph for talking about climate change is the global average temperature, which is shown here from 1893 approximately, or 1880, up to 2018 for this one. And you see that our current last September was the 416th consecutive month that we've been above the 20th century average. The forcings, what's causing this, we now know that human factors are the main factors that are driving it. This red curve here is the aggregate of all of the anthropogenic forcings, the one in the middle. You can see these spikes going down. It means that these are the factors that are cooling our climate, and the biggest one there are periodic volcanoes. So that's the spikes going down mean that the volcanoes put particles in the atmosphere that reflect sunlight and cool the planet for about a year, year and a half, and then the trend resumes whatever it was doing beforehand. If we look at, if we put those forcings on top of this graph, you can see that the upward trend is primarily caused by greenhouse gases. Well-mixed greenhouse gases, carbon dioxide, methane, nitrous oxide, CFCs, and so on, are the ones that we have high confidence now is really causing this. But if we look at other factors, for instance, we look at this one. This shows the times in history where we've had volcanoes in the last 60 years. So Mount Agung, 1983, El Chichon, 63, El Chichon, 83, and Pinatubo in 1991. Every time we get a volcano, you see there's a drop in the global average temperature. So we can see what the natural variability, the magnitude of the natural variability versus what humans are doing. If we look at the El Nino events, this is a warming in the global, or the tropical Pacific that leads to a temporary global warming. You see that, I haven't put them all on here, but you see that every time that these, or almost every time these occur, we see a warming. And on the other hand, we look at the ones that are indicated in blue. These are La Nina. These are cooling events in the tropical Pacific. They also affect our global average temperature by cooling it for a couple of years when they're active. So it underscores the fact that the natural variability is now small compared to the anthropogenic signal. So it's very clear. We are very confident. There is no convincing evidence for natural cycles in the observational record that could explain the observed changes in climate. And we have this at very high confidence. This is from the CCSP, the Climate Science Special Report. And I plotted here the carbon dioxide, the human-caused part is in the red. And if you look at the next two, solar and volcanoes, and the third one that I put on, they didn't put it on in the CCSP, but that's the ENSO, or the El Ninos, that the human causes are far outstripping natural variability. So it's very good, it's with high confidence that we know that humans are responsible for much of our change. So let's look at hot and cold days, precipitation, tornadoes, humidity, flooding, and then I'm going to talk about this concept of attribution to climate change. For any particular thing, like spring flooding is the one I'll look at. How confident are we that this is due to global climate change? That's the question I'm going to address. So just looking at the observed changes, again from the CSSP, I've indicated on each of these slides where they come from, except my own, which I think I might have overlooked. But so you can see the sources. You can go back and look for yourself and see the context. So this is a change in temperature, annual temperature in the big graph, showing that generally there's been pretty much uniform increase in temperature, at least in the west and the northern half of the country. In the southeast, we have, or in the south central and some parts of the southeast, we have a cooling actually going on, which is a little bit perplexing yet. We're reasonably confident it's due to aerosol particles that are not maybe treated quite right or have been maybe overlooked a bit in their the magnitude of their role. If we break it down by, and we see that Iowa has been a part of the warming trend, although part of Iowa is actually not warmed very much at all. But if we look at winter and summer, we see that Iowa has warmed a lot in the winter. Our winter temperatures have gone up. That's very clear. Our summer temperatures, on the other hand, have gone down. And we'll look at the maximum temperatures in particular, and we'll see, and we'll look at why that is. If we look at warmest and coldest days of the year, we see that the changes in the coldest temperature of the year have gotten warmer. That is, we don't get these minus 20 degrees Fahrenheit days for a week in a row like we used to back in the 30s and 40s and 50s. So our winter temperatures are much warmer than previously. Coldest day of the year has gone up by almost 3 degrees over this time period from 1986 to 2016 versus 2001 to 1960. On the other hand, the warmest temperatures have gone down. And so the challenge is for us as scientists to explain that. Is that really true, or is that part of natural variability? You see that the change in warmest day has gone down by about 2¼ degrees. We know that the length of the frost-free season has increased about 9 days in our regions. That's typical of the Midwest. And but if we look at the daily maximum temperature, and this is a plot that I produce and update every year. I take the current year and the preceding 9 years and call that the most recent decadal average. So this decadal average, because this is June, July, August, we've already seen that. So this is, actually this is only through 2018. So I guess I could update this one now. August is completed. But the interesting thing you see there is that our maximum temperature in the summer in the last 3 decades is markedly lower than the 20th century average. So we're in a period of global warming. We should be getting, it'd be intuitive to say that our summers should be getting hotter, but in fact they are not. If we look at the minimum temperatures during that same summer period, we see that in fact the minimum temperatures have gone up, daily minimum temperatures. So what's going on here? Is our climate actually getting more favorable? Well, in some ways it is. A recent study showed that 28% of our increase in corn yields in the last 30 years has been due to more favorable weather. Oddly enough, but primarily driven by precipitation. And so if we look at precipitation, we see that annually, the top graph shows that in green is more rain, brown is less rain. You see that we've had more rain. This is annual, so our annual totals have gone up. If you look at the breakdown by seasons, winter has been a little bit up, maybe on average, a lot of variability. Spring has gone up big time. We know that. You don't have to tell us that. Summer has gone up. We know that too. Fall is a bit of an enigma. We can see that Actually, in our region, the fall precipitation has trended down if we take the long-term view. Now, the past 2 years, this year and last year, are big counterexamples to that. And I don't really know what's going on there. I haven't figured that out. I've got to talk to somebody that's a lot smarter than me to figure that out. So, but it's a fact that we are now into, and whether this will be repeated again, I mean, 2 years is not a trend in climatological terms. We look at 30 years, we look at decades. So we can't really say if this is a trend, but it's noteworthy that in our past, falls have gotten more mild, which is better, of course, for harvest and for people and animals. That's something we really need to keep our eye on. If we look at statewide average, so this isn't one station, this is averaged over the whole state, we see something that's very remarkable. Again, I'm showing the 20th century average here at about 32.2 inches per year. And then we look at the last 3 decades, the average of that is 10% higher. 30-year average is 10% higher than the 20th century average. Remarkable on a climatological basis. We don't usually see that kind of thing. And the current decade, you see, is up over 37 and a half inches compared to 20th century average of 32 something. 5 inches above, almost 10%. Amazing. So it's no surprise. It's not a surprise, but it's good to put a number on it so that we can try to understand the more granularity of that in terms of what time of year and for what reasons, so that we can think about planning. The whole purpose of this conference is to think about planning, moving forward, coping with, building resilience. And so we need to know what we're building resilience to. And so hopefully these numbers will help us in understanding what these patterns are. If we look at extreme precipitation, the CCSP has a variety of ways of looking at it. I'm not going to explain all of these, but if we look at, they look at, for instance, the 5-year maximum daily precipitation, or the top 1%, which is in the right-hand column. That's one that I like to look at. And you can see that the dark blue is increases, and you can see that there has been a 42% increase in the percentage, the top 1%. So it's an astounding increase in the most extreme rain events that we have in our area, and also across the whole Northeast has followed that same pattern. Recent trends in tornadoes. I am always a little bit cynical about tornado statistics because, especially before 1950, tornadoes only occurred near major cities and interstate highways. So, and since then, wow, tornadoes have found the rest of the country. So we're a little bit cynical about some of these things, but here is a plot that shows us on the black curve the days of the year with at least one tornado. And you can see that that curve has kind of trended down, but if you look at the days per year with more than 30 tornadoes reported across the US, that is trending upward. Now, because of the problems in getting really good tornado statistics, we haven't spent as much time on that as we have hurricanes, but we know that hurricanes are getting stronger, and in some cases they may even be getting fewer, but they're certainly getting bigger. And maybe we're seeing the same kind of signal here with tornadoes. It's a little bit hard to speculate, but at least this is, we see that these clusters of tornadoes seem to be occurring with higher frequency. So let's look at floods. Floods are the big thing here. So I break it up into 3 different kinds of floods. I'm not talking about fall floods because I don't know what to say about that. But early spring floods, I'm talking about here February, March, April. These are from snow melt or rain on snow, and they're primarily due to melting of the December to March precipitation that falls outside of our state. Most of that is from outside of our state. And so that's where we see the problems with the Missouri River, the Mississippi River. If we look at the, oops, if we look at the Missouri River basin, it's a huge basin. Here's Iowa. And you see, here's Omaha, or Council Bluffs. You see this whole region that goes way up into Canada. All the snow that falls in that region comes down into the Mississippi, or the Missouri River. And so when it gets down to Omaha, we get the Platte River joining, the lower part of that, which exacerbates the flooding conditions in southwest Iowa. So, but it's snow that accumulates over the winter season, and then we get more variability in our winter climate, more quite warm days that occur in February or March. You get excessive melt, you get heavy rain on snowpack. It leads to extreme runoff and flooding along the Missouri River. The Mississippi River basin is much smaller, but yet there's a fairly large region up and through Minnesota, a small part of Wisconsin, that feeds into that leads to flooding on the Mississippi River. So we know the causes of that, and so that's mostly precipitation falling outside of the state. Now the spring and early floods, I'm talking about here, April, May, June. There's been a lot of study on that recently, and so we know that really quite well, and I'm going to talk about that. That's due to moisture coming up from the Gulf of Mexico on the Great Plains low-level jet. I'll just explain this and show it in a little bit. That comes up into our region, and then it's captured by this water vapor is captured by these mesoscale convective systems. That is, large systems that may be larger than a county and maybe even as big as a state, the whole state. And that processes this water and turns it into rain. If there's more water vapor coming in, you're going to get more rain coming out. It's a done deal. So we'll talk about those. We know quite a bit about that. And the stuff that we're getting now is, you saw it yesterday, you see moisture coming through, you see these little popcorn-style cells that pop up. Those are small mesoscale convective systems. They're not the huge ones, but they can bring 3.5 inches of rain to Des Moines. So let's talk about this winter-spring precipitation. First of all, this is the early season one. So we get warmer atmospheric temperatures due to climate change, due to global warming, which increases atmospheric water vapor. So we have warmer temperatures. It's evaporating more water over the oceans. So we have more water vapor in the atmosphere. And that's been measured. That's widely understood. And so there will be more water in the cycle. We say it speeds up or it intensifies the hydrological cycle. And then we also have more temperature variability due to global warming, which increases the likelihood that we will get warm temperatures during the time that we have snow on the ground. And so we can get more of these untimely early spring snowmelts or rain on top of snow. So it's very likely that these types of events are going to increase in our future. I'll take a look at the projections. I think the very last slide. We'll look at projections of what the precipitation is likely to be as we move forward to the middle of the 20th century. That'll come toward the end. So if we look at just the annual, again, this is April, May, June, precipitation and floods. So this is the whole record from 1893 to 2018. Actually, this is 2019. You can see that in the last 30 years, there's been an upward trend. And I just drew these on. These are not calculated by the graphing system. I just wanted to show that there's been some kind of a change. And if we look at the graphs on decadal averages, so we smooth out some of that variability, you see the same thing that we saw with the statewide annual totals. Here we have just the April, May, June precipitation. But again, you see the 20th century average, total for that period, 11.2 or so inches, three-month average. over the 20th century, that was normal. But now we're 2.2 inches higher than that for the last 3 decades. And the last decade, ending in 2019, is 20%, 27% higher than the 20th century average. An astounding increase on climatological scales. So looking at this, there's got to be a reason. We've got to understand the reason. Well, if we look at the humidity during that period, April, May, June, here's Dubuque, here's Cedar Rapids, Dubuque in the upper one, Cedar Rapids in the lower one. This is dew point, and you can see that that dew point temperature has gone up systematically since 1971. The absolute humidity, that is the amount of water vapor in the atmosphere, has depending on the location, it's gone up all through the state of Iowa in all seasons. So it isn't just April, May, June, it's even December, January, February. But you see, it's gone up in some cases as much as 4% per year, per decade. If you consider the planet has warmed by about 1 degree Celsius, then you can calculate from the Clausius-Clapeyron equation how much water vapor, extra water vapor we should have in the global atmosphere, and that comes out to be about 1% per decade, 1.2%. We're up to almost 4%, 4 times the global average. Little Iowa sitting here in the middle, far from the oceans. Why is our humidity going up so much during this time period? And is this going to continue? So there's been some really good research on this. Now this, don't panic, it's easy to understand if we just look at what we need to look at. So what we see here is this purple region in the center. This is the increase in humidity. This is a humidity trend in grams per kilogram per decade. So it's up to about 0.4, even 0.5 grams per kilogram per decade. That doesn't mean much to you, but you can see that we're in the bullseye on this. We're in the bullseye. Why did it pick on us here? This is trend. This is from 1979, 2014. Long-term trend. It's increasing. The hash marks there indicate this is high significance. This isn't just a fluke. It's high significance. Why? The planet is warming. The oceans are warming. The Gulf of Mexico is warming during this time period. So it's evaporating more water. Over the Gulf of Mexico, we have this huge dome of moisture piling up this time of year. We have a high pressure, the Bermuda High Pressure Center off the coast of the U.S. It is a permanent feature there, but I should say it's a long observed feature that comes and it goes and it comes, but when it's there, it sets up this clockwise circulation, and now it's been observed to be moving slightly westward. Then we have a low pressure center that forms over the Rocky Mountains. The Rocky Mountains haven't changed in the last 25 years, so that low pressure center is still where it was. So that's also, with the counterclockwise circulation, is amplifying the impact of the Bermuda High. That's always been here. We've always had this situation, but now it's being intensified, and we have then what we call the Great Plains low-level jet, which is responsible for the very favorable seasonal distribution of moisture that we've had. And that's why agriculture is so important to Iowa, because we have those heavy rains, those beneficial rains in the spring that recharge our deep soils, that provide moisture for corn going into the July and August dry seasons. It's beneficial. It's been there. That's why we raise these crops the way we do, and we get the yields that we get. But now, this Great Plains low-level jet is intensifying. 1.5 meters to 2 meters per second per decade on an average of 15 meters per second. So that's a 10% increase per decade in the moisture flow. There's more moisture down in the Gulf. There's a faster train that's getting it into our area. So then, it's there. Then we have these mesoscale convective systems that move across from Nebraska or Kansas into our area. We saw them track through last night. These are small ones, but they always have been there, and they are very efficient at processing rain. But when these thunderstorms come across Nebraska, it tends to be, on average, in the afternoon. It crosses the Iowa border at 6 o'clock or so at night. Normally, if you were in Colorado or Florida, those 6 o'clock thunderstorms would fizzle out, or would have already fizzled out. It'd be clear by 8 o'clock. Not so in Iowa. Here comes this stream of moisture, intensified at night. The low-level jet feeds right into these systems that would have died had it not been for this. Pumps new energy into these systems, and they explode at night, giving us these huge rains, many of them occurring after dark. In Ames, the maximum daily precipitation from these is at midnight. Well, then we get these mesoscale convective systems. Now, you've seen little popcorn stuff on radar last night. Look at the scale here, lower right-hand corner. That's Iowa down there, and over here is Nebraska, South Dakota, Minnesota. This is a huge system. It's almost, if it was parked over the state, it would almost cover the whole state. Copious amounts of rain. This is from August 2010. Anyway, we get these huge rains. So, summary then. April, May, June rainfall. Warmer Gulf of Mexico due to global warming. Westward shift, intensification of Bermuda High that strengthens low-level jet due to global warming. MCESs transform more humidity into rain. It's a pretty simple train of events. So, what can we expect into the future? Well, here's the projected mid-century precipitation change. This is from the, I don't have that indicated. This is from the Climate Science Special Report, CCSP. But you can see upper left is the winter, and lower right is spring. Green is higher, deeper green is even higher. Red stippled means that we have, that the models agree. 39 models were used here, and they all agree. You can see some hashed regions in the southern, southwest U.S. and surrounding. We have less confidence there. They indicate that these changes are small compared to natural variations. In the stippled regions, the changes are large compared to natural variations. So you can see that in Iowa and in our drainage basins in winter, it doesn't look good. It looks like more precipitation, more snow, more rain on snow during the winter season, extending on into the spring. You see the same thing. So with a reasonable amount of confidence, now, to have high confidence, see, I think I have this. No, I'm going to go to another example, then we'll talk about confidence. So here's the results of a study done with the Iowa Flood Center and the Iowa DOT to look at the bridge design to answer the question, how do we design bridges for the 21st century that will acknowledge what the best available science says the precipitation is going to be in the state of Iowa in the key basins that we need to think about bridge design. So this is for the Cedar River, designed for a bridge, Highway 30, which flooded in our most recent flood year. You can see that when we talk about, this is the metric, and I don't have time to deal with the details, but it's the annual one-day maximum averaged over the whole Cedar River Basin. And these are model, the blue is model projections, the red are the observations. You can see after 2000, that metric, that average rainfall over the basin went up dramatically. But you can see from the 19 global climate models that were used here, shown in blue, that, and this is a 90th percentile, 10th percentile, that the 90th percentile of the simulations that started in 1960 moving forward, so it got the model got the early part correctly, and it shows also that the 90th percentile just went way up after 2000. And so this is an independent way of looking at validating the climate science for this kind of bridge design. Well, I'll have to move along here. Confidence, how do we determine whether a particular climate event is due to climate change? Well, we have, we look at the evidence. How much, is there an established theory? Are there multiple sources? Are there consistent results? Are they well documented and by acceptable methods? And is there high consensus? Then we have high confidence. So we have ways of documenting how we rate our confidence in this. So applying those to our spring floods, this is my interpretation of using the National Climate Assessment methods. I say it's likely, not very likely, likely 60 to 100%. Recent trends and future projections of winter-spring precipitation in Missouri and Mississippi River Basin sort of give medium confidence that global warming contributes to our spring floods. If we look at the spring and early summer rains, I say it's very likely 90 to 100%, because the theory is good, the observations show it, the contributing factors are all there, and so it's very likely that our spring and summer, early summer floods are going to be with us for a long time. Just some future trends. Cold spells in the Midwest are the coldest day of the year by mid-century. It's probably going to be about 10 degrees warmer. Change in the coldest 5-day average, decadal average, about 15 degrees warmer. If we look at the heat, change in the warmest day of the year, 6.71, and the warmest 5-day event per decade, 13-degree rise in decadal, in 5-day average temperature. So those are very strong heating events that we're going to have to factor in the Midwest. Number of days above 90 degrees. Currently, we have 17 days per year, last 30 years. That will likely increase by to more like 57 by mid-century. Many more days above 90. Coldest days, 20 to 30 fewer days below freezing. Almost a month less below freezing. So we got to think about overwintering of pests. We think about hardiness zones. Lots of factors that are at play there. Length of the growing season will probably increase by about 20 days by mid-century. That'll open up a wide range of potential plantings or crops or even double cropping. So we need to think about that. Finally, projected precipitation, I've already shown you two. If we look at the summer and fall, well, we're seeing more of a drying pattern, although it's in that hatched area, which means that natural variability is high or higher than the projections. So just a little window into our future. Be happy to answer any questions, or you can see me later. Thank you.
You might just come up to the podium. Thank you, Professor Takle. So for those of us who aren't climate scientists, you at least reinforce that there's a reason that we're here and we weren't silly about coming and expecting to think about planning for future heat and flooding related events, and both the prevention and the mitigation that's going to come with it. We've got time for a couple of questions, and what we'll do is I'll bring this around. Excuse me.
Yes, I had a question about nighttime minimum temperatures and how that might be, if you've looked at that, and how that might impact some of these patterns as well.
Yeah, my first publication on climate change was in 1992 for the state of Iowa, and it said that projected that nights would warm more than days, summers would warm more than winters, and that's happened. That was 27 years ago. That's been consistent among all the models and the observations. And the reason is clear. With more humidity, we have more humidity that and water vapor, of course, is the major greenhouse gas. So if you have more humidity in the air, you're going to trap more heat at night. Nights in Iowa are different from nights in Colorado because of the humidity. It cools down very nicely in the dead of summer in Colorado. Not so here because of the high humidity. So as the humidity goes up, nighttime temperatures are going to go up. Pretty clear on that.
It looked like on one of your last slides that the Midwest one-day high average was going up more than in other sectors of the country. Is that because we're playing catch-up? Because our highs are relatively low now?
That's a very good observation. That's my interpretation, and that's what, in talking with the authors of the CCSP, well, the other authors, I was a part of that as well. But the people who are most knowledgeable about these and the global model trends is that we have been below, we've had this excess moisture which has kept our soils moist. So when the sun comes up in the morning, first item is it's got so much dew and water to evaporate that it has less energy to heat the air. And so the daytime maximum temperatures have been held down because of this excess moisture. Now, as we move toward the middle of the 20th century, we're going to have more ambient heat. The planet's going to be warming. There's going to be larger periods between these rain events, which means the soils are going to dry out, which means it's going to unmask this warming that's been going on, but we've been shielded from by this excess precipitation. Aerosols are in certain areas, like over India and over China. You can see from satellite pictures sometimes that there's just a haze of particles. Our Clean Air Act has really reduced the aerosols over the U.S., although there are natural aerosols as well. And so part of the cooling or lack of warming in the southeast is attributed in some regard to natural aerosols from forests and so on. So, but there is some uncertainty in the role of aerosols, and they themselves, if it's natural sources, they also are somewhat temperature dependent because it affects the biological system. So that's an area that we're trying to narrow the uncertainty on.
In our recent winter's polar vortex spell, is there some special relationship or attribution to a changing Arctic? Does that influence our winters?
Yeah, that's a very active area of research. Is the loss of sea ice and the general warming, the reduction in snow cover that is in the spring, for instance, so is that earlier warm-up, is that having some influence on global pressure patterns, temperature patterns, and therefore pressure patterns? The jury is still out on that. There is some evidence that there may be some kind of a delayed response, but the uncertainty is still very high on that. Polar vortex has been around for a long time too. It's become popularized by the media and so on. But it's real. I mean, it does drift away. And if the pressure patterns are not as intense, and the reason, even the early models, I looked at the first models back in 1988. I looked at the NASA models projections for the Arctic and said it would be a 10-degree warming with a doubling carbon dioxide. I said, that's crazy. I'm not going to show that in class. It'd be written off. We're on that track. And when that happens, when it gets warmer in the polar region without the comparable warming in the tropics, that means the temperature becomes more uniform. That means that the pressure gradients are reduced, which means that we don't have as strong a circulation as in the past. And that means that systems can migrate around more. They're not constrained by the jet streams like they have been. And so they're able to wander southward beyond their normal range a little bit. So that's what we're getting, the polar vortex coming into Iowa.
All right, please join me in thanking Professor
Thank you.
Takle. I understand.